Okie dokie. So Venema continues his look at neutral geometry, and so do we with section 3.5. Section 3.5 deals with a couple of theorems that we're going to need a lot of as the course goes by. No new axioms in this part. We've got the axioms that we need for a while. We're going to instead focus on how to apply those to get some big results that will then become foundational going forward. So here's the first one. It's an interesting theorem called the Z-theorem for reasons that shall become obvious in a moment. The Z-theorem says, let L be a line, and let A and D both be on line L. A is not equal to D. They're not the same point. If B and E are points on opposite sides of L, then ray AB and ray DE don't intersect. That's what the Z-theorem says. So let's take a look at the theorem. L is a line. A is on L. D is on L. A is not D. B and E are points on opposite sides of L, and remember what we mean by being on opposite sides of L. If we were to connect them with a line segment, it would cross line L. The segment would cross line L. So I want to show that ray AB cannot possibly hit ray DE. I want to show that this ray cannot possibly have any points in common with that ray. And it's actually not too hard to show. If ray AB is in half plane H1 and ray DE is in the other half plane, maybe that's called H2, then all of the points in AB are in one half plane and all of the points in DE are in the other half plane. I mean, that almost makes sense. Ray AB lives over here and ray DE lives over there. So the only place where those two rays could conceivably touch is at their endpoint. Well, here's the endpoint of ray AB, and here's the endpoint of ray DE, and guess what? They don't touch. So if these conditions are met, then we know, okay, the two rays cannot possibly intersect. It's called the Z-theorem for reasons that you're going to have to ponder. You're just going to have to ponder that. We really don't know why they call things the way they do. Now, we need that because we need this. If ABC is a triangle and D is in the interior of angle BAC, then there exists a point G such that G is on ray AD and G is on segment BC. It's called the crossbar theorem for reasons that will become obvious in a, oh, let's go black. I have some triangle A, B, C, and I have some point D that's in the interior of angle BAC, not necessarily in the interior of the triangle, but in the interior of the angle. The theorem works the same. What we argue is that this ray has to intersect segment BC at some point. And because I should have known what's coming, I'll just move this over just a scotch. Okay, so here's what we do with this picture. This is one of those things that almost makes sense, and when something almost makes sense, that's a good thing. That gives us a chance to determine, does this have to exist? Must there be an intersection? And so this isn't too bad. Here's what we do. We extend BA this way to some point E, and we extend segment AC this way to some point F. So far, so good. We can do that. We can extend segments along a ray, we're okay. Now, we apply Pasch's axiom to triangle EBC. Pasch's axiom is going to say, I have some giant triangle EBC, and I have some line, this line, that intersects one of the sides of triangle ECB. It is known to intersect segment EB. And so we know by Pasch that it either has to hit EC or it has to hit CB. That's Pasch's axiom. I've got a line, it hits one side of a triangle, it's got to hit one of the other two. What we want to show is that it is BC. So we therefore have to show three things. We have to show that ray AF doesn't hit segment EC. We have to show that ray AF doesn't hit segment BC. And we have to show that ray AD doesn't hit segment EC. If we can prove those three things, then we will prove that AD has to hit BC, and that's the way it goes. Oh, man. Oh, I did that sort of wrong. Okay. It's okay. AF is an extension of AD, not of AC. My apologies. The proof is still going to work exactly the same way, but we should recognize that AF is an extension of ray DA, not of ray CA. So sorry to all you folks watching at home. So let's go after this one at a time. First things first, I want to show that AF and EC never intersect. And the way to show that AF and EC never intersect, I'm imagining, is going to come from this. Oh, look, it's a Z. Oh, look, it's a Z. So why does this work? A is between F and D. By construction, A is between F and D. So F and D lie on opposite sides of EB. Okay, F and D lie on opposite sides of EB. But D and C are on the same side of EB by construction. So since C and D are on the same side and F and D are on opposite sides, F and C are on opposite sides. And if F and C are on opposite sides of EB or EA or whatever, then by the Z theorem, AF never hits EC. Doesn't hit the ray, therefore it doesn't hit the segment. The second one is going to come similarly. The Z looks like this. In this case, we can make a similar argument that F and C are on opposite sides of line EB, and you can think that argument through, but with F and C on opposite sides, we're good there. The third part comes with this Z. Right? Yes. And I'll let you think about why that is true. But if we get a Z that way, we show that AD cannot intersect EC. That's the way that goes. E and D Oh, no, that's not true. E and D are on opposite sides of AC. E and D are on opposite sides of AC. And you should think about why that is true. I'll let you think about that. And if not, you can just read it in a text. That's neat. So the red thing is true, the blue thing is true, the green thing is true, and so we get the intersection that we're looking for. Okay? Okay. We should pause at this point to consider some things. Because we have angles and angle measures and things crossing, we should revisit a picture that should be familiar from high school. So you have A, B, C, and D, and you have these two angles right here, and we called those two angles a linear pair. And we loved linear pairs because what do we know? We know that this angle and that angle add up to 180 degrees, and therefore they are supplementary. So we should know what a linear pair is. We should know what supplementary angles are. Of course, getting there is more than half the fun. Getting to a place where you actually have linear pairs that add to 180 degrees, that's a big deal. And to do that, we need a lemma first. The lemma says if A is between C and B, and if D is in the interior of angle BAE, then E is in the interior of angle DAC. And again, this is one of those things that actually makes a whole lot of sense, and that's good news. There are two must-shows here that get the job done for us. One is to show that E and D are on the same side of line AC. If E and D are on the same side of line AC, then some wonderful things happen. And that's what angle interior definitions are all about. The other thing we have to show is that E and C are on the same side of line AD. If E and C are on the same side of AD, that sticks E squarely in the interior of angle DAC. So we need E and D on the same side of AC so that we can talk about angle interiors at all. And then we say, okay, if D is in the interior of BAE, and we have E and C on the same side, then E's got to be in the interior of angle DAC. Okay? Okay. Again, the lemma is not that hard to walk through. D is in the interior of angle BAE by assumption. And so E and D are on the same side of line AB. So this part leads to this. D can't be in the interior of BAE without that being true. And so line AB is the same as line AC is the same as line BC, and so we're good to go on the red stuff. And that means, oh goodness sakes, here comes crossbar theorem. AD has to intersect segment BE. If we were to draw segment BE in, AD would have to intersect it. And if AD intersects BE, then B and E are on opposite sides of this ray. And if B and E are on opposite sides of this ray, that's good, because we already know that B and C are on opposite sides of that ray. So if B and E are on opposite sides, and B and C are on opposite sides, then E and C are on the same side. And if E and C are on the same side, then we're all done. We are all done. We've got what we want. So from that lemma, we lead to here. If angle BAD and angle DAC form a linear pair, then the measure of BAD plus the measure of DAC is 180 degrees. And Venema walks you through a proof, and I'm going to ask you to read that proof. One, for the sake of time. Two, because it's good to learn how to read mathematics. You should recognize that the proof follows a familiar rhythm. And the rhythm is, if I want to show equal to 180, I try less than, show that doesn't work, and I try greater than, show that doesn't work. When you have eliminated the impossible, whatever remains, however improbable, must be the truth. That's the way that proof goes. It's an entire page typewritten. A couple of things to think about that we will talk about when we come to class. What does it mean for two lines to be perpendicular? What does it mean to draw a perpendicular bisector, and how do I know that any segment has to have a perpendicular bisector? Likewise, this is something you probably hit in September of the year you took geometry in high school. What are vertical angles, and are they congruent? And if they're congruent, why are they congruent? Those are all things to think about. And I know most people talk about perpendicular bisectors in terms of triangle congruence. We haven't established triangle congruence yet, so we can't talk about it that way. Ha 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 ha. Okay, so that's all for now, and we'll do 3-6 next time.